Here we're going to analyze the relation between the correlation energy and the correlation Hall. Again, the exchange and correlation energy function can be decomposed in the exchange energy and the correlation energy. We already analyzed the relation between the exchange energy function and the exchange Hall, and now we are going to center analysis on the correlation energy, which is going to be much more complicated. So first, that's the definition of the correlation energy function, which basically is everything which is not included in the exchange energy and the Hartree energy, and also in the kinetic energy, because when doing the constant method, we are just considering the non-interacting, the kinetic energy of the non-interacting system. But in the physical system, of course, we do have the kinetic energy of the physical interacting system. So there's a difference between the two. So that everything which is not included in all these expressions means the following. So basically, the correlation energy function, it can be it's defined as the average of the kinetic energy and the electron potential energy when considering the physical ground state wave function, minus the average of the kinetic energy and the electron potential energy when considering the Kohn-Sham wave function. So therefore, we do have like two different contributions in the correlation energy function. One is going to be associated to the kinetic energy difference, and the other one is going to be associated to the potential energy difference. And on the other hand, we do have a correlation Hall, which is of course going to be related to the exchange and correlation Hall that we defined in order to describe the reduced pair density. And the exchange and correlation Hall, it can be decomposed in two different contributions. One is going to be the exchange Hall and the other is going to be the correlation Hall. Actually, the exchange Hall was actually used in order to analyze the exchange energy function. And this reduced exchange and correlation Hall actually has some interesting constraints. And for example, one of these constraints is the following, that when doing the integration over r prime, it's equal to -1. And actually, that constraint is also it's already fulfilled by the reduced exchange Hall. So therefore, the remaining constraint for the correlation Hall is this one. It basically means that the integration over r prime of the reduced correlation Hall is equal to 0. That basically means that the correlation Hall has either positive and negative contributions. Okay. So first, we are going to consider the contribution or an expression for the correlation energy the potential energy contribution to the correlation energy function. And that's what we have here. So by definition, this is the potential energy contribution to the correlation energy function. So basically, it's the difference of the average on the potential energy or the electronic potential energy when considering the physical ground state wave function and considering the Kohn-Sham wave functions. So again, here is everything which is not included here. And here we were including the Hartree contribution, we were including also the exchange contribution. So when writing that one in terms of the reduced pair density, we can write the reduced pair density in terms of the exchange, in terms of the density. And the remaining part, which is not included in the Hartree and the exchange contribution, is therefore the correlation Hall contribution. So therefore, it's very easy to see that the potential energy contribution to the correlation energy functional can be written in this way as a function of the reduced correlation Hall here. But this is just for the potential energy contribution to the correlation energy function. And what about the kinetic energy contribution here? That's going to be tough to do. That's really difficult to do. So in order to write that correlation energy functional here in a similar form as we are doing here for just the potential energy contribution here, we need the adiabatic connection formula. Why is that? Because here in this adiabatic connection formula here, we are writing the correlation energy functional just as a function of different averages of the potential energies. So there is no contribution here on the of the kinetic energy. So this is the good thing. And the bad thing is that we need to do this average for different lambda from 0 to 1. So what we can do is we can write actually that difference in the same way as we did it here for different lambda, so that instead of writing the difference just as a function of the reduced correlation Hall, we could write it as a function of a lambda dependent reduced correlation Hall. So we can write that difference here as a function of the lambda dependent reduced correlation Hall. And this is what we have here. So considering the adiabatic connection formula before, we could write that difference as a function of the lambda dependent reduced correlation Hall. And we need to do the integration over lambda from 0 to 1. But the lambda dependent is just on this term here, which is this lambda dependent correlation Hall. We are making that, we have to do that integration here. So we are going to call this one, which basically this is that one, we are going to call it the coupling constant integrated correlation Hall. So considering that, we are able to write all the contributions to the correlation energy function, both the kinetic and the potential energy contributions, in the similar way as we did for the exchange contribution, but in terms of this Hall here, which is a coupling constant integrated correlation Hall. So that according to that, it leads to interpretation of the correlation energy function as the electrostatic interaction energy of an electron with its coupling constant integrated electron Hall. So if we want to make an approximation for the correlation energy functional, we need to have a good approximation for that coupling constant integrated correlation Hall. In the same way as we did for the exchange energy functional, we could also write the correlation energy functional in this way as the density times some function and integrate over R, so that function, which is actually the correlation energy per particle, it's considering that expression here is just basically this one. So either the correlation energy functional or the correlation energy functional per particle, both can be written in terms of the coupling constant integrated correlation Hall, actually in the similar way as we did for the exchange energy functional. But for that, in this case, we needed the application of the adiabatic connection formula, because the correlation energy function not only depends in principle of the potential energy, but also depends on the kinetic energy. And in order to have a closed expression just in terms of the potential energy, we needed the application of the adiabatic connection formula.